Hello everyone. So today we'll continue with the next lecture on pre-stressed concrete. That is, we have already started with the first method, that is your stress method. So we have already seen one numerical on that. So let us continue with the second numerical. So I'll just read out the question. So a rectangular concrete beam of cross section 30 centimeter deep and 20 centimeter wide is pre-stressed by means of 15 wires of 5 diameter located at 6.5 centimeter from the bottom of the beam and 3 wires of 5 diameter at 2.5 centimeter from the top of the beam. Assuming pre-stress in steel as 840 MPa, calculate the stresses at the extreme fibers of the midspan section when the beam is supporting its own weight over a span of 6 meters. If UDL of live load of 6 kN per meter is imposed, evaluate the maximum working stress in concrete. Take density as 24. So let us just write down the given data which is given in the question. So at first the dimensions of the section is given to us. It is 20 centimeter wide and 30 centimeter deep. That means 200 wide and 300 deep. So as you can see, I have drawn the cross section, and the steel is given as 15 wires of 5 diameter. So 15 wires of 5 diameter, they are located at 6.5 centimeter from the bottom. So that means 65 from the bottom. So you can see in the figure. So I have drawn that, and at the top there are 3 wires which are of 5 diameter and located at 25 from the top of the beam. And the span of the beam is 6 meters. The live load is 6 kilonewton per meter, as you can see in the figure. Pre-stress is given as 840 Newton per mm square, and the density of concrete is 24. So what we have to find out, we have to find the stresses, that is F top and F bottom. Two conditions are given. First is transfer stage and the second is service stage. So transfer stage means only pre-stress plus self-weight. Service stage means pre-stress plus self-weight plus live load. So let us go to the solution part now. So the first step here is, first we will find out the distance of the centroid of the pre-stressing force from the base. Okay, so it is given by Varignon's theorem, that is principle of moments. So moment of forces at the base is equal to moment of resultant at the base. So which gives you 15 into 65. 15 is the total number of wires and it is at a distance of 65 from the bottom, and plus 3. 3 is the number of wires and its distance from the bottom is 275, that is 300 minus 25 is equal to moment of resultant is total number of wires is 15 plus 3 18 into y is the distance which we want to find out. So y is 100 So listen, actually we can find out this y also like you find out your normal y bar. So in this case the area is constant, so they have eliminated that part. So what you can do is you can just find out the y bar, which is given by a1 into y1 plus a2 into y2 upon a1 plus a2. So a1 is nothing but the area of the steel at the bottom and its distance from the bottom y1, and a2 is the area of the steel at the top and its distance from the bottom, and divide by a1 plus a2. So your a area is common, so that gets cancelled out and you get the value of y is equal to 100 So I hope it is clear now. So now eccentricity is nothing but the distance distance from the neutral axis. So E is equal to d by 2, that is 150 minus y bar. So we got the eccentricity. So why we calculated the centroid of the pre-stressing force? To actually get the eccentricity. So now once you got the eccentricity, we will find out the pre-stressing force. So pre-stress initial pre-stress is given to you. So if you know the stress, you can find out the force. Area of steel bars is also given to you. Total area is 18 into pi by 4 into 5 square. So that gives you P, the value of P as 300 kilonewton. So now let us go to the second step, that is to find out the section properties. So again in section properties we'll find out the area, moment of inertia and section modulus. So we get area, and I is nothing but BD cube by 12 where B is 200 and D is 300, and Z is nothing but I by Y. So we got the properties of the section. So now we can go to the next step, that is to find out the loads and moments. So first we'll find out the self weight of the beam is given by nothing but cross section dimension into the density. So it is 1.44, and live load is given in the question, which is 6 kilonewton per meter. So total load is nothing but the addition of dead load and live load, which comes out to be 7.44. So now bending moment at the center of the span is given by the total load, that is W into L square by 8 for a simply supported beam. So we got the bending moment 33.48. So now we can actually find out the resultant stress. So in the question we have to find out for two stages, that is first is transfer and then second is service. So first we'll find out for the transfer stage. So F top is given by P by A minus PE by Z plus mg by Z. So whenever it is asked for separately for transfer and service, you can keep your dead load bending moment separate and live load bending moment separate. So I have calculated mg dead load bending moment separately. So your mg is nothing but 6.48. So you have to calculate that separately. And similarly F bottom is nothing but P by A plus PE by Z minus mg by Z. So your F top is 2.46, that is compression, and your F bottom, since the value is negative, so it is tension. So now let us go to the second part of the question, that is to find out at the service stage. F top is given by P by A minus PE by Z plus M by Z. So remember, this M is the total, that is mg plus mq. So either you can write it as mg plus mq, or you can directly write it as m by z. So I got F top as 11.16 and F bottom as minus 1.16, that is in tension. So this is how you're going to solve this problem. So I hope it is clear now. To find out the resultant stress, first you will find out the eccentricity. For the eccentricity we had to find out the distance of the centroid of the pre-stressing force from the base, and the rest of the procedure is similar as we have done in the first question. So now let us go to the second question. Okay, so now in this we are going to solve an unsymmetrical I section. So very important question. So if you solve this, you'll be able to solve the symmetrical I section also. So I'll just read the question. An unsymmetrical I section beam is used to support an imposed load of 2 kilonewton per meter over a span of 8 meters. The sectional details are top flange is given and the bottom flange is also given to you. Thickness of the web is 80 mm. Overall depth of the beam is 400 mm. At the quarter of the span, the effective pre-stressing force of 100 kilonewton is located at 50 mm from the soffit of the beam. Estimate the stresses at the quarter span section of the beam for the following load conditions. So now they are asking to find out the stresses at the quarter span of the section. So now we'll see how to solve this. So again there are two conditions. First is pre-stress plus self-weight, that is your transfer stage, and the next is pre-stress plus self-weight plus live load, that is nothing but your service stage. So let us draw the figure what is given in the question as per the given data. So 300 by 60 is the top flange, bottom flange is 100 by 60, and the web is 80 by 200. So I hope this is clear. And the span of the beam is 8 meters and the live load is 2 kilonewton per meter and the effective pre-stressing force is 100 kilonewton. So first we will find out the section properties. So the first step you'll always do is to find out the section properties. So what we are going to find: area, your y bar, your moment of inertia, and your section modulus. So since this is an unsymmetrical I section, you'll have to calculate everything. So first let us calculate the area. So let us divide this I section into three rectangles. So the first rectangle is 100 by 60, the second is 80 by 200, and the third rectangle is 300 by 60. So I have just calculated, okay, I have taken the first rectangle as 300 by 60. So if you add all these rectangle areas, you will get the total area. The next is to find out the y bar of the section. So y bar is given by a1 into y1 plus a2 into y2 plus a3 into y3 upon a1 plus a2 plus a3. So the one which I was referring to in the previous question, you can find the centroid with the help of this formula also. So now you get y bar as 243.96. This is from the bottom. Okay, so from the top it is nothing but total 400 minus 243.96 will give you the y bar from the top. So since it is symmetrical about the y-axis, so x bar we already knew, but it is unsymmetrical about the x-axis, so we have calculated the y bar. So now we can actually find out the eccentricity of the cable. So eccentricity of the cable is given by 243.96 minus 50. So it is given in the question that at the quarter span of the pre-stressing force is located at 50 mm from the soffit of the beam. So with the help of this, we got the eccentricity is nothing but the distance of the CG of the steel from the neutral axis. So neutral axis we have found out, that is y bottom, it is from the bottom, it is 243.96. So eccentricity we got it as 193.96. Now let us find out the moment of inertia about the x-axis. Okay, so moment of inertia about the x-axis we have located. So it is given by your parallel axis theorem. So it is nothing but ixx1 plus ixx2 plus ixx3. So we have selected the first rectangle as 300 by 60. So I have done accordingly. So first we will find out for the first rectangle. So ixx for that rectangle is nothing but bd cube by 12. So 300 into d is 60 cube by 12 plus area is nothing but a into h square. So a is 300 into 60 and h is, remember, h is the distance from the x-axis of the unsymmetrical eye section to the x-axis of that particular rectangle which we are dealing with. So the x-axis of the first rectangle is nothing but the center of 60. Half of 60 is nothing but 30. So if you subtract 30 from 156.04, you will get the distance from the two parallel axes, that is the axis of the unsymmetrical eye section and the axis of the first rectangle. So I hope it is clear now. Now for the second rectangle, let us see 80 into b is 80 and d is 280 cube by 12 plus area is 80 into 280 and the distance is 243.96 minus 200, that is h square, a into h square. Similarly for the third rectangle, it is bd cube by 12, that is b is 100, d is 60, bd cube by 12 plus area is 100 into 60 plus again this, the axis of for this rectangle is at the center half of 60, that is 30. So 243 minus 30 is your h. So now we got your ixx, that is 757.46 into 10 raised to 6 mm raised to 4. So now we will find out the z, that is section modulus. So since you have different y bar, yb and yt, so you will have zt and zb. So zt is given by ixx upon yt and zb is given by ixx upon yb. So we got the values of zt and zb. Now the next step is to find out the loads and moments. So first we'll find out the dead load of the beam is given by area into density. Area we already know, density is already given in the question. So we got the dead load as 1.11 kilonewton per meter. So please remember the units and then find out the dead load. So live load is also given to you 2 kilonewton per meter. So the moment due to dead load is, I am just finding out separately mg and mq. So wg into L square by 8. So now to find out the dead load bending moment at the quarter span of the beam. So if you remember in the question, it is asked to find the stresses at the quarter span. Can you see here, to find the stresses at the quarter span? So that is the reason we are first finding out the moment at the quarter span of the section. So mg at the quarter span, so this is the beam of span 8 meters and wg is 1.11. So first you have to find out the reactions. Reaction is nothing but 4.44 and then at the quarter span of 8 is nothing but 2 meters. So at xx you have to find out the moment. So that is nothing but 4.44 into 2 distance and minus w into x by 2, where w is 1.11. So you got the bending moment at 2 meters, that is at the quarter span. Similarly mq at the quarter span you will get it as 12 kilonewton meter. So now you can find out the resultant stresses. So you've got all the values. So case 1 is pre-stress plus self weight. So f top is given by p by a minus PE by ZT plus mg by ZT. So you got the value of F top, which comes out to be negative, that means it is tension, and F bottom is 6.26, that is positive, that means compression. So now we'll find out for the second case. The second case is nothing but pre-stress plus self-weight plus live load. So here you will also consider the value of MQ. So it is better that you keep it separate so that you don't make mistakes. So I have done it separately, P by A minus PE by ZT plus mg by ZT plus mq by zt. So this, remember this to find out the values of all the fractions separately, so it will be better so that you won't make any mistakes. So it comes out to be 2 and F bottom is 2.32, so both are in compression. So in the working stage it is, at the top it is 2 and at the bottom it is 2.32, and at the transfer stage it is 0.47 at the top and 6.26. So this is your final stress distribution diagram, that is resultant stress of the section. So I hope it is clear now. We have solved 3 problems on stress method, and I think it is more than enough for you as far as your exams are concerned. Thank you.